Our intermediate value theorem states for if A and B are not the same and A happens to be less than B, if f of A and f of B have opposite signs, then the function has at least one zero on the interval. Let's look at an example of that. Let's say f of 2 would equal negative 11, but then f of 3 equals 4. If the graph is continuous and there's no holes or jumps, then what does that mean? What happened? What can we guarantee? Well, what it means is that we guaranteed to have something go through the x-axis at least one time. If you think about f of 2 being negative 11, 1, 2, negative 11 way down here, f of 3, 4. Again, if it's a continuous function, maybe it's a curve, maybe it's a line, maybe it went through there a couple of times. But at the end of the day, it had to go through there somewhere at least one time. So there, to be honest, there isn't a ton of, there is times when we want to use this idea, but it just, again, does it get us an x-intercept or not? So number 5, show that this function has a 0 on the interval of negative 4 and negative 3. So what we're going to do, plug in negative 4. If we plug in negative 4, we'll get negative 9. If we plug in negative 3, negative 3 to the 4th plus 6 to the negative 30 cubed minus 26 times negative 3 plus 15. I'll save you the work again. You're going to get 12. So what do you notice about these two results? They're opposite signs. We got one point that's above the y or the x-axis and one point below the x-axis. Therefore, if it's a continuous function, it had to cross the x-axis somewhere. So notice signs changed. Therefore, graph must cross x-axis. So what does that mean? Do we have a root or a 0? Yeah. So at least 1 0. Could we have more than one? Sure. It would be very tight or very small, but it's possible to have 3 or 5 or whatever. Maybe a touching point in there as well. We don't know what the scenario is exactly, but there is at least one. Good on that idea? So with all of this in mind, we are now going to go ahead and start to develop a general sketch of what these polynomial functions may look like. Okay, and this goes back to all the skills that we've been working with for the last couple of days now, going back into last week. Number of turning points of a polynomial. A graph of a polynomial f with degree n has at most n minus 1 turning points. Okay, so let's take a look at our parabola. Parabola, we just looked at it, has a degree of what? 2. So our n is 2. So at most n minus 1, so 2 minus 1, at most 1 turning point. And that makes sense. The only turning point that we have on the parabola is there at the vertex. So there's an example of that. We could look at a cubic function. A cubic function may look something like that. And how many turning points do we have here? 2. Turning points are when it changes from an increasing to decreasing or vice versa. So our turning points are there and there. There are hills and our valleys. Okay. So again, n minus 1, 3 minus 1, 2. We have at most 2. you know, sometimes you'll have a, you could have it where this is actually a cubic function too. Notice really no turning points, but again, this rule just stipulates at most n minus 1. So not going to tell us exactly how many, but we know it's never going to exceed the n value. Good on that. So we're going to keep that in mind as we go into it. And now as we turn to the next page, we have this huge checklist, so to speak, of all the different things that we've been going through. All right. I'll be honest with you, we're not going to hit every single one of them exactly. There's just kind of main ones that I want us to look at. That leading term is obviously going to dictate that end behavior, kind of where it starts at, so to speak. So number 1 will be a good one. You know, determining your y-intercept is always good. Just evaluating for f of 0. That can be a simple yet effective point to have, kind of keep in our back pocket. Determine the real zeros. You know, anytime I can find the x-intercepts, I think that can be helpful as well as the multiplicities. We talked about that on Friday. Even multiplicities is a touching point. Odd multiplicities is a crossing point. So we'll plot those x and y intercepts along with the end behavior. 5, 6, and 7 gets kind of long, but I'll just, again, let's do this. Cross the x-axis with an odd multiplicity. Touch with an even multiplicity. We have those rules in place there too. We could look for symmetry. If we know that it's an even function, it will be symmetric about the y-axis. And if it's an odd function, if we knew that, again, symmetric about the origin then. And then number 7 is just saying, okay, if you need to plot more points, if you need to get a better description of it, you can always plug in x and solve for y. But we're probably not going to be doing a lot of that. So this is a very general scheme to sketching this. But again, the idea when we're all said and done is we can take certain aspects, things that we know or things that we found, and we can apply that to the graph and say, yep, that point's going to look like this, or yep, it's going to be a crossing point, and so forth. So let's go through a couple of these together and you'll get the idea. Negative x cubed plus 4x. What's our degree, odd or even? Odd. Very good. Odd means same or opposite direction? Opposite. Very good. Which means we have one of two options. It could be left end could be up and the right end could be going down, or left end going down and right end going up. Which one of these two options do you think it is? Remember? First one? It is the first one. And the reason being? Yep. Leading term is negative. Therefore, the left end is going to start high and the right end is going to finish low. Think about your, slope of a line again, our most basic. If it's a negative slope, it's going to go down from left to right. So same idea, the left end is going high, bottom end is going down. So left end up, right end down. And notice I kind of numbered these out for you to kind of help you out. 1, yep, there we did that. Leading term along with end behavior, that was the rule. Number 2, up on top, determine the y-intercept. 2 down below, y-intercept here, just plug in x equals 0. Negative 0 cubed plus 4, 0. Gets us 0. So what's our y-intercept then? 0, 0. So we can go ahead and plot that point. It's going to go through the origin. About some zeros here. maybe we'll go ahead and do some work down below here. 0 is equal to negative x cubed plus 4x. All those years of solving equations still around. How we go about solving this one? Step 1. What do you think, Maya? All right. We see the x cubed, and that can be a little misleading. Thing I would tell you is if you have any common factors, don't be afraid to get rid of those extras, or the trash, so to speak. So I do see the two terms and an x in each one of those. So maybe if we factored out an x, better yet, maybe a negative x would help us out. So I did factor out the negative so that this x squared on the inside could be positive, minus 4. X and x2 and 2 plus minus 0, negative 2, 2. There it is. So again, 0, negative 2, and 2. What were the multiplicities for each of these? 1, very good. I didn't talk about this. This is actually getting into the fundamental theorem of arithmetic, but what should your multiplicities always add up to? Do you know? Any guesses?
The degree.
Yes, your degree. Our degree here for this guy was 3. That's our highest exponent. And notice 1 plus 1 plus 1 gets us that degree of 3. So all zeros accounted for. What does this imply about all these zeros? Crossing or touching points? Crossing. So maybe we want to make note of that. All of these are crossing points. So we can actually, because they're zeros, we know they're going to be x-intercepts. We can go ahead and graph those. So negative 2. Yep, we already have 0. We knew that was going to be the y-intercept. Just so happens to also be the 0. So there are those points there. So sketch the zeros and the end behavior. Odd and even multiplicities, we talked about that. They were all odd. Very good. And now let's go ahead and do it. Left end is going to start by going up. We need to go through this point here. Now we don't know how far down it's going to go, but we'll just say it's about right there. We'll go back up through 0. Just crossing point again. It's going to go up so far and then has to come back down. So again, the whole idea is, from the skills that we now know, hopefully we could create a general idea of what that polynomial will look like. Let's do one more. We'll move a little quicker here. Number 1. Leading coefficient. So notice for this one, they give us the factored form. Do you remember how to find that leading coefficient here? Yeah, you got to multiply all the leading terms here. So 0.5 x times x times x. And do we got to do it twice? Yeah, there's 2 of them. So we're going to get a couple of things here. One, we're going to get that leading term to determine whether it's positive or negative. Just so happens to be positive. And then 1, 2, 3, 4 x's. we are also going to get that degree of 4. So degree is 4. It's even. So again, it's either going to be up, up, or down, down. For our left and right, which one is it? Up, up, because it's a positive 0.5. Hopefully all of that's coming back to us. So our left and right end behaviors up and up. Kind of like a parabola. 2, want to find that y-intercept where x is 0. So f of 0, or h of 0, I guess. 0, 0 minus 1, 0 plus 3. 0 minus 1, negative 1, times 3 squared, which is 9. Wait. But all of that gets multiplied by 0, right? So it doesn't matter. It's just 0. Kind of overlooked that. So once again, we're going to have the origin be a part of the graph. And I'm going to let you go ahead and finish it. Find your zeros, identify multiplicities, and go ahead and come up with your sketch. Zeros, I came up with 0, 1, and negative 3. Agree? Multiplicity for 0, I believe, is 1. I think that's 1. What's your multiplicity for negative 3? 2. 1, 1, and 2 adds up to what? 4. And we said at the beginning we did have a degree of 4, so that's good. We're kind of doing step 5 here, but this will be a crossing point. At 1 will be a crossing point as well. But how about at negative 3? That is a touch point. It's going to either come down and touch it and go back up, or it's going to come up, touch it, and then go back down. So I think we're good to go. 5, we talked about that. Touch versus crossing. Don't have to worry about that. Did that up there. 6, there is no symmetry here. And 7, I don't think it's needed. You're going to get to the point where you don't even need this checklist. I mean, it's provided to you to kind of help you get started, but you just kind of know what you're looking for. Yeah, got it all. We're good to go. 0, 1, and negative 3. And we said the end behavior's got to be up and up. So, lastly, negative 3 was a touching point. So the left end's going up, come down, we're gonna touch at -3 and then go back up. But eventually somewhere it's gotta turn and come back down. And then after we go down, we gotta come back up and we'll finish by going up. And that would be a perfectly acceptable sketch of the graph right there.